Okay, lesson 3, pendulums. So a pendulum is just a string with a mass attached to the bottom, and these things swing back and forth. The mass at the bottom is what's called the bob of the pendulum. And then there's also something called the equilibrium position. This pendulum here right now is in the equilibrium position. And the reason for that is it's hanging straight down. So this one is not in the equilibrium position because it's not hanging straight down, but this one that I drew a line pointing to is. So here are those definitions. You can pause the video and write them down. So we're studying pendulums here because pendulums conserve mechanical energy. The word mechanical means total. So pendulums conserve total energy. As long as no friction acts on a pendulum, it will conserve mechanical energy because it's a closed system. So I want you to imagine a pendulum swinging back and forth. You can watch this YouTube video if you want to see a pendulum swinging back and forth, or you can just imagine it. And I want you to think about where is the pendulum moving the fastest and where is it moving the slowest. So here I have a picture of a pendulum. We're going to indicate where its speed is highest and lowest. So at positions 1 and 5, for a second, the pendulum actually stops. Because at positions 1 and 5, that's where the pendulum has reached its maximum height. And when things reach maximum height, for a split second, they stop. And then at position 3, that's where the pendulum is moving the fastest. And of course, at positions 2 and 4, it would be sort of like a medium speed. Okay, and so what's happening here is that the pendulum, when it's on the way down, is speeding up. And the pendulum, when it's on the way up, is slowing down. So we can explain what's happening with the speed there in terms of energy. So during the downswing, when it's moving down, it's losing height, right? So that means it's losing gravitational potential energy. So gravitational potential energy is going away because it's being converted to kinetic energy. And so on the way down, because the pendulum is gaining kinetic energy, it's also gaining speed. And then on the upswing, it's the opposite. So on the way up, kinetic energy is transferred back into gravitational potential energy. So what we need to know is that the pendulum has the most gravitational potential energy at positions 1 and 5. And again, that's because gravitational potential energy depends on height, and it's going to have the most kinetic energy wherever it's traveling the fastest. And since it's traveling fastest at position 3, that's where it has the most kinetic energy. Now we can also see this graphically. So let's suppose that we're looking at a case here where there's a closed system, so there's no friction. Okay, here these are our positions. So remember I had that pendulum and it was labeled 1, 2, 3, 4, 5. This would be like 1, the middle would be 3, the end would be 5. So 2 and 4 would be somewhere in between. And what we can see here is that the purple line represents the mechanical energy. So this is like the total energy. So if you look at the purple line, it is just staying the same as time passes, right? It's not getting bigger or smaller. And that's because mechanical energy is conserved. But if we look at the red line, let's say, at position 3, right here, the red line is nice and high because that's where kinetic energy is high. And then at positions 1 and 5, the kinetic energy is low. And then the potential energy is doing the opposite. So the potential energy is the blue line because as kinetic energy goes up, potential energy has to go down. And something else to know from this, so let's say that we look at numbers. So let's say that right here, this is 10 joules, just as an example. If we pick anywhere on the graph and we draw a vertical line through it, let's say that right here, this amount is 2 joules. Well, then this number here would have to be 8 joules, because if 10 joules is the total energy, 2 joules plus 8 joules would need to be 10 joules. And we could do this anywhere, right? So we could also do this here. This would be 10, this would be 0. 10 plus 0 is still just 10. Now I want to just show you what this graph would look like if we had an open system instead. So let's say we have a situation where friction is acting. So let's draw a new graph. You can just fit this in somewhere on your page. We're going to have energy in joules on the y-axis, and we'll put position on the x-axis. So like before, we'll label this with our 2 positions. This time, for the mechanical energy, as time passes, the mechanical energy is going to be decreasing. So this is the mechanical energy. So now we're saying that the system is losing energy as time passes. Okay, and then we're going to have our 2 other lines. So this is going to be potential energy that I just drew. And then something like that for kinetic energy. So if you're looking at a graph and you're trying to determine whether it's an open system or a closed system, you really look at this mechanical energy line. If the mechanical energy is flat, then it's a closed system. But if the mechanical energy is angled, either up or down, then it's an open system. So now we're going to take a break from talking about the energy acting on pendulums, and we're going to look at the forces acting on a pendulum instead. Here I have those 5 positions again. So I want you to notice that in each diagram here, the force of gravity is directed down and its magnitude never changes. So if we look at the force of gravity in diagram 1 and we compare it to the force of gravity in diagram 3, for example, those arrows are the same. And then now we'll look at tension. So we remember from our dynamics unit that tension is directed along the string. So that means that the direction and the magnitude of the tension actually changes depending on the pendulum's position. So if we look at position 1, the tension's a bit shorter. If we look at position 3, the tension is longer. And so when we have a pendulum and it's displaced from its equilibrium point, a restoring force tries to bring the pendulum back to the center. And the further the pendulum is from the equilibrium point, the bigger the restoring force is. So that means position 3 is the equilibrium point. So that means at position 3, there's no restoring force. But at positions 1 and 5, the pendulum's really far away from the equilibrium point. So at positions 1 and 5, there would be a big restoring force. And at positions 2 and 4, there'd be still a restoring force, but smaller than at positions 1 and 5. So on this diagram here, we're supposed to indicate where the restoring force is large and where it is 0. So the restoring force is large at positions 1 and 5, and it is 0 at position 3. Now, the other thing we learned in the dynamics unit is that force and acceleration are linked, right? So we know, because of this formula here, F net equals ma, that when acceleration goes up, force also goes up. Well, actually the other way around. When force goes up, acceleration goes up. So wherever the force is large, the acceleration should be large too. So that means the pendulum's acceleration should be high at positions 1 and 5, because that's where the restoring force is big. And the pendulum's acceleration should actually be 0 at position 3. Now you'd have to be a little bit careful with this. Don't mix up acceleration with speed, because they are 2 different things. At position 3, okay, we have 0 acceleration, but at the same time, we have a high speed. So that seems kind of contradictory. But remember, acceleration is really a measure of how much the speed is changing. So what's happening here is that in the areas sort of right around position 3, the speed doesn't change very much. Whereas from like 4 to 5, for example, or from 1 to 2, the speed changes a lot. So from 1 to 2, there's a big change in speed. And from 4 to 5, also a big change in speed. But right around position 3, there's not much change in the speed. Okay, that's not the same thing as saying that the speed is low at position 3. So this is like saying from 1 to 2, we're maybe going from 0 meters per second to 10 meters per second, just as an example. That's a big jump, but the speed is still 0 at position 1. And then maybe from position 2 to 3, we're only going from 10 to 11, let's say. And then at position 4, back to 10, and then at position 5, back to 0. So you'll notice that from 2 to 3, the speed only changes by 1 meter per second, okay, which is less of a change. However, the pendulum's still moving fastest at position 3 and still moving slowest at positions 1 and 5. Okay, so now we're going to try to calculate the restoring force. So restoring force is really like the net force acting on a pendulum. So here we have a picture of a pendulum, and we want to try to calculate the net force acting on it. So in here, we've got Fg, and then that's already been broken down for us into Fgy, and then this one, just temporarily, we're going to call it Fgx. And then we also have our tension force right here. So what happens here is that the tension force and Fgy cancel each other out. They're balanced forces because they're the same number of newtons, but they're in exactly opposite directions. And so if Ft and Fgy cancel each other out, then the only force that's left is Fgx. We're not considering what's happening with Fg here because Fg has been broken down into components. So we only need to look at the components, not actually Fg itself. So Fgy is gone, Fgx is left. That means that the net force here is Fgx. But looking up here, for a pendulum, we have a special name for the net force. It's called the restoring force. So we can write Fr. Okay, now we know that Fgx is going to be sine of theta times Fg, right? So we can put all of this together and we can say that our restoring force is, I'm just going to write it in a different order, Fg sine theta. So if you're asked to calculate the restoring force on a pendulum, that is the formula to use. So let's see how to use this formula here. So it says determine the acceleration of a 300-gram pendulum bob as it passes through an angle of 10 degrees to the left of the equilibrium point. Okay, just a hint for you. In lesson 3, there's going to be some questions that ask you to find acceleration of a pendulum and other questions that ask you to find the speed of a pendulum. If you're asked to find acceleration, you need to use restoring force. So acceleration and force go together. If you're asked to find the speed of the pendulum, then you need to use energy. And that's what we'll do in tomorrow's lesson. We'll revisit the idea of energy and do some examples together. But here, because it asks me to find acceleration, I should use restoring force. So not doing anything to do with energy here. So I know that the restoring force is Fg sine theta. This is going to be the same thing as mg sine theta because Fg is equal to mg. So now we just have to put our numbers in here. When you're doing this, make sure you work in kilograms, not grams. So 300 grams is the same thing as 0.3 kilograms. G is 9.81. And then we're doing sine of 10 degrees. Need to make sure you're in degree mode. And when you do this, you should get 0.511 newtons. So that is the restoring force on the pendulum. We can also think of it as the net force. However, we know that net force is equal to ma. So we can rearrange for A. A is going to be F net over m. And this is going to be 0.511 newtons divided by 0.3 kilograms. And after rounding to 2 significant digits, we want 2 sig digs because the angle here is 2 significant digits. We're going to get 1.7 meters per second squared. Okay, you try this question on your own and then try doing the check your understanding as well. And that's going to be it for part 1 of lesson 3.